The transformer architecture has been a huge breakthrough in AI. Due to this, large language models have become incredibly powerful. They can generate human-like text, translate languages, summarize articles, answer complex questions, and even write code. Their ability to understand and generate text with high accuracy has revolutionized the way we interact with AI. First, large language models tokenize the text, breaking it down into smaller units called tokens. Then, these tokens are converted into embeddings. If you're unfamiliar with embeddings, I have explained embeddings in detail, and I suggest you to watch the embedding before watching this video. Embeddings transform text into high-dimensional dense vectors that capture the meaning of each token. For example, the word cat has an embedding vector close to similar words like dog and rat. These embeddings come from an embedding matrix, where the number of rows equals the total vocabulary size, and the number of columns represents the embedding dimensions. As we discussed in the previous video, each token has its own embedding lookup position. So words like apple, orange, and banana are close in embedding space because they are all fruits. The embedding has learned this relationship. However, there's a problem. Embeddings alone do not distinguish between words with multiple meanings. For example, in our text, apple refers to the tech company, not the fruit. But the embedding table assigns a single embedding value for apple, regardless of context. Ideally, we want the embedding of apple to adapt based on its meaning and context. In this case, it should be closer to other tech companies rather than fruits. This is where self-attention comes in. The self-attention mechanism transforms semantic representations into contextual representations, making sure words are understood correctly in their specific context. Self-attention is extremely powerful. It was introduced in the paper Attention is All You Need, where the transformer architecture uses attention mechanisms in both its encoder and decoder. In the architecture, it first tokenizes the text, then get embeddings that capture semantic meaning, and finally, apply self-attention to incorporate contextual meaning. So now you know what the attention mechanism does. Let's understand how it works. In the paper, self-attention is represented by this equation. Let's write it down on our screen. To understand this, we first need to understand what query, key, and value are, as shown in the equation. To get context information, a single token interacts with other tokens and assigns weights to each of them. Then, based on these weights, it takes a proportionate amount from each token to form a new representation that contains contextual information. So these different values for a single token, query, key, and value, each have their own role. Using the same method, all tokens interact with each other, assigning importance to each token. This assigned importance is called the attention weight, which determines how much a token attends to another token. Now let's understand query, key, and value in detail. We start with token embeddings. From these embeddings, we derive three new vectors: query, key, and value. These are high-dimensional vectors like embeddings, but have different values and are unique to each other. If we have three tokens in a text, each token has its own query, key, and value vector. When a token needs to interact with other tokens to determine the weight assignment, it uses its query vector. For example, if token A wants to determine how much weight to assign to token B, it uses its query vector as if asking, "Hey, do you have anything useful for me?" In response, token B uses its key vector to answer, "Here's what I can offer." We then take the dot product of these two vectors, query and key, to obtain a scalar value which gives a score. This score tells us how well token B matches token A, in order to help create a new representation for token A. Each token follows this process, asking itself and all other tokens for scores to determine how much they match. A simple and efficient way to do all of this at once is by performing matrix multiplication between the query matrix, which contains all tokens' query vectors, and the key matrix, which contains all tokens' key vectors. We first transpose the key matrix and then perform matrix multiplication. The result is a set of scores that each token receives from all other tokens. The scores obtained after multiplying the query and key matrices are called attention scores. For two tokens, we get 4 different values. If we have 5 tokens in a text, we take a query matrix containing all the query vectors and a key matrix containing all the key vectors. After transposing the key matrix to match the shape, we compute 25 attention scores, since each token interacts with all other tokens to determine what information is useful for forming its new representation. Now you understand query and key. The query is used to ask for information, and the key is used to provide that information, resulting in the attention score. The value matrix then helps us compute the final representation. For example, to create a new representation for the word apple, it first interacts with other tokens. Then, using the computed attention scores, it determines how much importance to assign to each token. Based on these values, it extracts the corresponding portion from each token's value vector to form a new contextual embedding. Now that you understand the purpose of query, key, and value, let's see how we can obtain these vectors. Now that we have an embedding for each token from the embedding layer, we transform this embedding using weight matrices. These matrices are specifically for query, key, and value. After applying these transformations, we obtain the query, key, and value vectors for each token. These weight matrices are trainable parameters, meaning they are learned during training. Their purpose is to transform the original embeddings into meaningful query, key, and value representations. When I say these weights are learned and transform the embedding into its own query, key, and value, I mean that a neural network with linear activations is used to train and optimize them over time. Once we obtain the query, key, and value vectors, we compute the attention scores by multiplying the query and key matrices. A high score means the token assigns more importance to that specific token. After obtaining these scores, we use them along with the value matrix. The value matrix is obtained by multiplying the embedding with the weight matrix of value. This is then used along with the attention scores to get the final contextual embeddings. So a quick recap here. To get a new contextual representation for the token apple, it first queries all other tokens, then gets the scores, and finally uses the appropriate proportion from each token to get the final representation. The value each token assigns to other tokens is called the attention weight. These weights follow a specific pattern, and we use this pattern to compute the new embedding. Up until now, this is the overall process, but there is one more step left. So far, we have used the query vector to ask other tokens and the key vector to answer. We then multiplied them to get the attention score. However, this is not the final value that we multiply with the value matrix. If we look at the attention equation, after multiplying query and key, we divide by a certain value and then apply the softmax function. Only after this step, we multiply with the value matrix to get the final representation. First, let's understand what softmax does. Softmax is a mathematical function that takes a list of numbers and converts them into a list of values that can be interpreted as probabilities. However, softmax has a problem. When given a list of numbers with a high range or large variance, it assigns a very high weight to the largest number, while the others get values close to zero. On the other hand, if the input numbers are very small or similar, all values become almost equal. To handle this issue, we normalize the attention scores by dividing them by the square root of the dimension of the key vector before applying softmax. This ensures that the final attention weights are well balanced. The reason for using the square root of the dimension of key is to keep the attention scores at a reasonable scale so that softmax does not become too sensitive to large values. The exact mathematical reasoning behind this is beyond our discussion here, but in simple terms, it helps balance the scaling effect as the dimension of key increases. In the original paper, they mentioned that the dot product of query and key is divided by the square root of the key dimension to counteract the effect of increasing attention scores when the key dimension grows larger. So if this is our raw attention score, we first divide it by the square root of the key dimension to normalize it. After applying softmax across each row, we get values that sum to 1 and act as the attention weights, representing how much importance each token assigns to the others. For example, here token A assigns 25% importance to itself, 1% to token B, 68% to token K, 5% to token D. This tells us how much token A attends to each token. Similarly, token C here assigned 26% to itself, 1% to token D, and so on. In this way, we can interpret the attention weights. Now let's summarize the steps. First, we multiply query and key to get the raw attention scores. Then we scale the scores by dividing by the square root of the key dimension. Finally, we apply softmax to get the attention weights. Now that we have attention weights, we use them along with the value vector to compute the final embedding. Each token now uses its attention weight to determine how much it should take from other tokens. For example, token A assigns 60% weight to itself and 40% weight to token B. Token B assigns 70% weight to token A and 30% weight to itself. We take that proportion of the value vectors and sum them up to get the new representation for each token. This entire process is actually just matrix multiplication. Taking the weighted sum of each token's value is done using matrix multiplication. So after multiplying the attention weights with the value matrix, we get the weighted sum, which results in the new contextual embeddings for all tokens. Now you know what query, key, and value are, how we generate them, and their roles in the attention mechanism. This entire process, from transforming the embeddings into query, key, and value to scaling and normalizing to computing attention weights, and finally taking the weighted sum, is the self-attention mechanism. Self-attention is what transforms a static embedding into a contextual embedding, allowing us to get a meaningful representation of text that captures relationships between words. In the decoder architecture of a large language model, there is a variation of self-attention called causal self-attention. In the dataset preparation video, I mentioned that we prepare training data by selecting a context window, here size of 10, and setting the training label as the next token in the sequence. The reason we do this is to train the model to predict what comes next given the provided context. This is a classification task, but unlike regular classification tasks in large language models, we do not just predict the next token after the full context. We train the model to predict the next token at every position in the sequence. This means that for each token, the model learns to use the previous words to predict what comes next. As a result, the label size is the same as the training token size, but the labels are shifted one step ahead of the input tokens. Now let's take a simple training example with a context size of 5. First, we tokenize the text and obtain its embedding vectors. After that, we compute the query and key vectors and use them to calculate attention scores. However, there's a problem here. Since each token in a language model is trained to predict the next token, the first token should only be using itself to predict the second token. But when calculating the attention score, we are allowing the first token to attend to all other tokens, meaning it already has access to the token it is supposed to predict. Similarly, the second token is attending to its target token, and so is the third token, meaning all tokens are looking ahead into the future. Only the last token should be allowed to attend to all previous tokens, because it uses the full context to predict the next token, which is not in the context window. To prevent tokens from attending future tokens, we use a mask of the same size as the sequence. This mask contains negative infinity values in the positions where tokens should not attend. We then add this masking matrix to the original attention score, effectively replacing the values that represent attention to future tokens with negative infinity. The reason we use negative infinity is that when we apply softmax, these values will effectively be ignored and become 0, ensuring that the tokens do not assign any weight to future tokens. Here, the first token will give 100% weight to itself, because all future tokens are masked. The second token will attend only to the first and itself. The third token will attend only to the first two and itself, and so on. Applying softmax to the masked attention scores row by row gives us the attention weights, and this method is called causal self-attention, which prevents tokens from attending to future tokens. After this, the process remains the same. We use the attention weights to compute a weighted sum of the value vectors, giving us the final contextual embeddings. For a sequence of n tokens, the attention matrix is n times n, so doubling the context size results in 4 times more attention scores. As the context size increases, the attention weight matrix grows quadratically in size, meaning the number of attention scores that need to be computed and stored increases rapidly. This leads to higher memory usage and computational cost, making it challenging to scale transformers to very long sequences efficiently. Now let's understand multi-head attention. So far, we have seen a single self-attention mechanism that takes embeddings and produces contextual embeddings. But in transformer architecture, instead of using a single attention head, multiple self-attention mechanisms are used in parallel. The idea is that instead of performing a single attention operation to get the contextual embedding, it is beneficial to linearly project the query, key, and value using different learned linear projections, which are lower dimensional, and then concatenate their outputs to get the final embedding. Here is the equation for multi-head attention. Let's write it down. The reason for this is to capture different aspects of relationships between tokens. A single attention head may focus on word meaning, while another may focus on syntax and another on long-range dependencies. This allows the model to understand different perspectives of the input simultaneously. Let's assume the embedding size of our model is 512. We use 4 attention heads, and each head has an inner dimension of 128. This means that for each attention head, the query, key, and value vectors will have a dimension of 128 instead of 512. Additionally, we have another new weight matrix, WOut, which is the output projection. The weight matrices for query, key, and value are the same as in self-attention, but now each attention head has its own learnable weights and projects the input into a lower dimension. Each individual attention head works exactly like the self-attention mechanism we discussed earlier. It computes attention scores, applies softmax, takes a weighted sum, and produces an output embedding. Since we have 4 attention heads, this process is repeated 4 times, each with its own learned projections. After that, we concatenate the outputs from all heads, resulting in a 512-dimensional vector, which is the same as our original embedding size. Finally, we apply a linear projection using WOut to get the final contextual representation. The reason for doing this is that it allows the model to combine information from multiple attention heads, capturing different types of dependencies between words. This is how multi-head attention works. We take multiple self-attention mechanisms, each with its own learnable weights for query, key, and value. Each head produces an output embedding in a lower dimension. These outputs are concatenated and then linearly projected to obtain the final contextual embedding. This is multi-head attention, and it is represented by this diagram in the transformer architecture. Now that you understand multi-head attention, let's see where it is used in the transformer architecture. The transformer architecture applies multi-head attention in both the encoder and decoder. In the encoder, it uses multi-head attention. Here the attention is not masked and allows to attend to all other tokens. In the decoder, it first applies masked multi-head attention right after token embedding. Then, another multi-head attention layer follows, which we call cross-attention. It is called cross-attention because it allows the decoder to focus on different parts of the encoder's output rather than just attending to itself. This helps in sequence-to-sequence tasks like translation, where the decoder needs to extract relevant information from the encoder's representation. Here it gets key and value from encoder, and it uses query its own decoder. However, since we are focusing on large language models, which only use the decoder part of the transformer, cross-attention is not needed here. The architecture also includes layer normalization and residual connections in a specific order. This specific architecture is GPT-2 Model. GPT-2 Small Model has embedding size of 768, context size of 1024, 12 decoder layers, and 12 attention heads. Let's see how the input tokens flow in the architecture. First, 1024 tokens are sent into an embedding layer, which acts as a lookup table for all tokens in the GPT-2 tokenizer. Each token receives its embedding vector, and positional information is added. The result first goes through a layer normalization step. In this normalization layer, the model normalizes the activations of each input token across all features. This ensures that the values remain in a stable range, preventing the issue of exploding or vanishing gradients. It does this by computing the mean and variance for each input token, and then adjusting the values to have zero mean and unit variance. This helps the model train more effectively and speeds up convergence. Importantly, the shape of the input remains unchanged because normalization only affects the values, not the structure. After this, the tokens pass through multi-head attention. A residual connection is added here, ensuring the shape remains the same due to element-wise addition. Layer normalization and residual connections are also found in other deep learning architectures. Their purpose is to stabilize training, allow better gradient flow, and ensure that important features are retained across layers. Residual connections specifically help in preventing the problem of deep networks struggling to pass information effectively by allowing the gradient to flow through multiple layers unimpeded. Here, another layer normalization follows, again keeping the shape unchanged, before passing through a feed-forward neural network. Now comes the feed-forward neural network layer. This feed-forward network applies a transformation that expands the input representation into a higher dimensional space, allowing the model to capture more complex relationships. Then, it reduces the dimensionality back to its original shape so that it matches the input. This means the overall structure remains the same while enriching the token representation. Another residual connection is applied here. If you observe, the output of the decoder has the same shape as its input. This output is then sent to the next decoder layer and is repeated multiple times. In GPT-2 Small, we have 12 identical decoder layers, each learning new patterns and capturing different levels of context. After all decoder layers, we apply a final layer normalization followed by a linear layer. As I explained in my previous embedding video, this linear layer functions similarly to the initial embedding layer, but instead, it outputs logits for the next token prediction. In GPT-2, the weights of the embedding layer and final linear layer are shared, meaning both the start and end of the decoder influence the embedding process. The logits are then passed through a softmax function to obtain a probability distribution over all possible tokens. Using labeled data, we calculate the loss at each token position to predict the next token. We then compute gradients and apply backpropagation through all the layers, updating the model's weights. Each decoder layer is repeated multiple times, with each layer learning different aspects of language. The multi-head attention mechanism captures different levels of context in different decoder layers, but we don't fully understand why large language models scale so well and what these attention mechanisms learn. Now that you've seen all the trainable parameters in the model, you understand why these models have millions and billions of parameters. This is just GPT-2 Small. In modern large language models, we see thousands of context size, hundreds of attention heads, dozens or even hundreds of decoder layers, embedding dimensions in the tens of thousands. This is why we don't just call them language models, we call them large language models. That was a short summary of GPT-2 architecture with the attention mechanism. Hope you enjoyed the video. Thank you for watching and see you in the next one.